Have you ever stopped to think about how your TV signal actually gets to you? I mean, it goes from a studio, shoots up into space, and then zips right back down to your living room, all in the blink of an eye. Well, today, we're diving into the incredible story of how we figured out how to teach television to beat the curve of the Earth itself. Let's jump in. So, to really get why we needed satellites, we have to rewind a bit. We have to go back to this huge, fundamental problem that early TV had to deal with. And it was a problem that was literally baked right into the planet. You see, TV signals, they act a lot like light. They travel in perfectly straight lines. But of course, our planet is a giant sphere, and that created this massive headache for the first broadcasters. A transmitter on the ground could only send a signal about, say, 50 to 100 kilometers before that signal just kept going straight, right off into space, completely lost over the horizon. It left huge, vast parts of the world totally disconnected. And then someone asked this incredibly simple but absolutely brilliant question that changed everything. If the curve of the Earth is the problem, what if you could just bypass it? What if you put the broadcast tower somewhere impossibly high, somewhere not on Earth at all? And, well, that's exactly what we did. The solution wasn't about building a taller tower on the ground. It was about building one up in the heavens, a truly celestial solution to a very earthly problem. And you know what's wild? This completely revolutionary idea came from a science fiction writer. All the way back in 1945, the legendary Arthur C. Clarke imagined putting a relay station in a very specific spot in space. It was an idea that sounded like pure sci-fi, but it was really just brilliant orbital physics in disguise. Now just let that number sink in for a second. 35,786 kilometers. Straight up, that is the magic altitude. And it's not some random number, it is the absolute perfect height where a satellite's speed matches Earth's rotation, creating this kind of perfect cosmic dance. And this gets us to the key idea behind the whole thing: geostationary orbit. At that exact height, a satellite is moving so fast that its orbit takes exactly 24 hours, the same time it takes the Earth to spin. So from our perspective down here, it looks like it's just hanging there, perfectly still in one spot in the sky 24/7. It becomes, for all intents and purposes, a permanent tower in the sky. So here's the beautiful physics behind it all. You've got Earth's gravity constantly pulling the satellite inward, right? But at the same time, the satellite's incredible speed is creating a centrifugal force that's trying to fling it out into space. At exactly 35,786 kilometers, those two forces are in perfect, exquisite balance. The result? A satellite that seems to hover, able to beam a signal down to almost a third of the entire planet all at once. Just amazing. You know, the very first TV satellite, Telstar 1, back in '62, was a huge deal, a massive first step. But as you can see, it was in a low orbit, which meant it would just zip across the sky, and you'd only get these short little windows of transmission. Now compare that to a modern geostationary satellite, which gives us constant 24/7 coverage over an entire continent. It really shows the huge leap from a cool experiment to a powerful global system. Okay, so we've got our tower in the sky. Now, let's actually follow the signal on its epic journey. We're talking a round trip of over 70,000 kilometers that happens in just a fraction of a second. It's basically a four-step dance. First, you have the uplink. A giant dish at a broadcast center shoots the TV signal up into space. Step 2, the satellite catches it, works a little magic, and Step 3 sends it back down in the downlink. And finally, Step 4, your little dish at home catches that faint signal, and a decoder box turns it all back into the show you're watching. It's incredible. So let's talk about the heart of the satellite itself, this thing called a transponder. It has three very simple but totally crucial jobs. First, it receives the signal from Earth. Then, and this is clever, it shifts the frequency, so the new signal it sends out doesn't interfere with the one still coming in. And finally, it amplifies it, giving it a massive power boost for that long journey all the way back down to Earth. For a long time, this amazing technology was just for huge corporations and governments. But then, a revolution happened, a breakthrough that basically put a personal broadcast tower on top of millions and millions of homes. Yeah, this revolution really kicked into high gear in the 80s. That's when digital compression came along, which meant we could suddenly squeeze way more channels into a single signal. Then in the 90s, the tech got so good that smaller, much more affordable dishes could pick up the signal. And that was the birth of direct-to-home TV, or DTH. It was a total game changer, especially for connecting rural and remote communities. So how in the world does that dish on your roof actually work? Well, it all boils down to this really elegant principle of physics and geometry. That parabolic curve, that bowl shape, it's not an accident. It is a perfect signal-catching machine by design. Okay, think of your dish like a super-powered magnifying glass, but for radio waves. By the time the signal gets here from space, it's incredibly weak. So the dish's job is to collect all those faint waves spread out over its surface and focus them all down onto one tiny, single spot, that little thing at the end of the arm, the LNB. The LNB then boosts that signal and sends it down the cable to your set-top box, which finally decodes it all back into picture and sound. It's just a marvel of precision engineering. All right, so you might be thinking, in an age of nonstop internet streaming, is satellite TV even still relevant? And the answer is, without a doubt, yes, because this technology is constantly evolving. And this is where you really see the key difference. Look, streaming is fantastic for watching what you want when you want, if you've got a great internet connection. But satellite's killer app is its universal reach. For broadcasting a huge live event, like the World Cup final, to an entire country at the exact same moment, or for reaching places where broadband is flaky or just doesn't exist, satellite is still the undisputed king. And this technology is not standing still, not by a long shot. The next generation of satellites are way more powerful and way smarter. They're using incredible tech like beam-forming antennas that can target signals with pinpoint accuracy, almost like a spotlight from space. We're even seeing these cool hybrid systems that use satellite for live TV and your internet for on-demand stuff, basically giving you the best of both worlds. So when you boil it all down, it's an amazing story. We started with a problem caused by the very shape of our planet, and we found a solution that required us to leave it behind. The story of satellite TV is really a triumph of human imagination, and it just goes to prove that sometimes the best way to connect everyone in the world is to go very, very far away from it.